All right. Good to see you all. We are here to explore the third programming language concept in CS2104. We have discovered the syntax of programming languages. We have looked at control. And control is an aspect of the semantics of programming languages. Typically, we are talking about dynamic semantics or the runtime semantics of programming languages when we talk about control. Today, we're looking at a different semantic aspect of programming languages that is sometimes referred to as the static semantics. That means semantics that you can actually explore without talking about running programs. We will take a closer look at types. So I'm going to go through some motivations for the types. Then we look at different categories of types. We look at a bit of a landscape of what kinds of types do we have. The types of types. And then we look at typing strategies. That means we're looking at different ways programming language designers have made sense of this notion of types. Look at a bit of theory, just to give you a rough idea of what's going on. And then we look at a couple of more advanced topics and an outlook. So motivation. What is the purpose of types in programming? Now, when you look at computers, the actual processing unit in our computers have very little information about what kind of data they are treating. So at the end of the day, when you're looking at particular registers or particular memory locations, they are containing sequences of bits, and those bits do or don't make sense depending on how you look at them. And how you look at them depends on what instructions are involved in executing or accessing those bits. So in a way, when you, as a programmer, you're thinking of data structures, you're thinking of stuff in your mind. What is actually happening in the computer is detached from your imagination. So there are two things. One is what the kind of things you have in your mind when you're talking about data, and the other thing is what actually happens in a computer. The computer, roughly speaking, zeros and ones, and no data structures, and your mind contains all these fancy ideas. So data are products of our imagination, roughly speaking. And a mismatch of our imagination with reality leads to errors, bugs, right? So if something happens in a computer that is not consistent with your imagination of what should happen, what kind of structures you're dealing with, you are encountering errors, you're encountering bugs. And some of these bugs we call type errors. So the idea here is to prevent some kind of bugs. The bugs that result from this mismatch between our imagination and what happens in the computer at the right time. We prevent those bugs by imposing a discipline. We're imposing a type discipline on different kinds of components of this whole process. You could impose a discipline on compiling your program. So the compiler could enforce a certain discipline. But you could also impose a discipline on the runtime system. You could say, oh, okay, I don't prevent this bug before I run the program, but when I run the program, I make sure nothing totally terrible happens. So I'm sort of channel this bug in the right direction. So there are different approaches here, how we can prevent bugs at different stages of our program execution pipeline, which we covered when we discussed these T diagrams, right? So at different stages, you could deal with this mismatch of our imagination with what actually happens in the computer in different ways. But it's always done by imposing a discipline. We are restricting what we can do when we are dealing with types. We're restricting what a particular runtime system is allowed to do, or we're restricting the way programmers can write their programs. So it's always, and that's a common theme in computing. Can I have your attention, please? Yeah? There's a common theme in computing that we are imposing restrictions in order to gain benefits. We are imposing a particular structure in our database, right? So you're coming up with a relational database that imposes a very specific structure on our knowledge. And what do we gain from this? Well, you can do SQL, right? You can access this data structure in a very disciplined and systematic way. It's a common theme. We're imposing structure. We're imposing structure in computer networks, right? You are describing different layers, like you're describing the protocols that happens. Protocols are constraints. They are disciplines that we are imposing on the way we communicate. It's a common theme throughout computing. The world out there is wild and woolly, and it's very hard to understand. So let us simplify things. Let us impose discipline. Let us impose constraints. And these constraints are our friends. They're not out there to hurt us. They are out there to help us. And that is the case for types as well. Types are there to help us deal with this mismatch between our imagination and what happens in the computer. So more specifically, we categorize data according to types, and we enforce adherence to these categories. So we are using tools to impose that structure, to enforce these constraints. And the benefits are that some of these errors don't occur or are much less likely to occur. Other uses, apart from helping us with this mismatch, other uses of types are documentation. If you are writing a program and you are using a language that forces you to describe these types, these descriptions can be part of your documentation. Another advantage of types might be in implementation. So a programming system is able to take those types and use them to improve the performance of your program. So these are other benefits that we reap when we're using types. All right, so the next section, we are looking at categories of types. What sorts of types do we have? What are the things that we're talking about when we are talking about types in programming? So here I'm looking at primitive types, I'm looking at type constructors, and other ways to combine types into bigger types. Let's look at primitive types. In most programming languages, you have a notion of types that don't have further structure. So if you're programming in, let's say, Java, and you have a double precision floating point number in Java, or a long integer, you know what you're talking about, you know what operations apply, and typically we don't look further inside of those things. They are atomic, and as it comes to types, they are considered primitive. So I included strings here, although usually we have access to these strings and can look inside of them. So are strings primitive in a sense of types that might be considered primitive, in that they are considered atomic entities, but we can take a look at them and take them apart. In some languages, for example in C, a string is just an array of characters, and in that sense, a string could also be a compound type, as we will see them in a few more minutes. So strings with a bit of a question mark here. In programs, you can actually write down these types. You can specify in your programs, in some languages, that particular things in your program should be associated with these primitive types. So we give names to these types. That's what I'm saying. So in programs, we can refer to these primitive types using particular names like int, float, or string. There are also enumerated types. That means there are types that you, as a programmer, can define. So for example, in C, you have an enum type. Enum type color, red, green, blue. These are constants that you are defining in the language using an enum type, and you can use them in the rest of the program as primitive values. Or simple data types in SML. So in SML lets you describe data types quite similar to enum types in C by listing the constants that are allowed in place of, in those places in which color items are allowed. So here we're talking about languages in which these types are part of the programming language. We can associate names in programs with types, and then we can restrict the way these names are used such that these type declarations are adhered to. More about that in the section typing strategies. But yeah, so there are these enumerated types. That means we can explicitly list the constants that a type is associated with. These data type declarations in SML, by the way, are a lot more powerful than this. And the assignment that we get this week will explore SML in detail. So you will learn a bit of SML in this coming assignment. So that's something to look forward to for next week. Other languages have range types that let you specify particular ranges in numerical values. For example, you can write range 0.9. That's the range of digits from 0 to 9. And in Ada, you can give a name to that type. And that then lets you actually come up with programs in which very specific restrictions apply. So, for example, in Java, you can declare an numbers of type byte, and that means you have only 8 bits available, and these numbers are meant to range from -128 to +127. And if your operation exceeds those, if your operations exceed those limits, you can handle them specifically like this. So you can raise an exception if your ranges are violated. And I believe that if you have operations that violate these ranges and go beyond the byte limits, you get a runtime exception as well. That's what I think should happen. There will be particular instructions in the Java virtual machine that will raise these exceptions, but we can verify that. So enumerate the types that you explicitly list the values that are associated with specific types, so that these constraints can apply. Another category of type are Cartesian product. So here we're looking at forming tuples out of simpler types. So here we have the type string in the language Pascal, and we form a tuple of strings. So in this case, we have 4 different components in the tuple: first name, surname, address, and position. The first name, surname, and position are strings. The address is an array of strings. So we have other types, like string, array of string, that can form the components of a more complex type, in this case, a record. And you have a particular syntax that lets you access the components of a data structure. So that's a typical operation that we have in type programming languages. We can form bigger types out of smaller types by aggregation. Aggregation in the sense that we aggregate various components into a larger structure. Tuples, records, those are typical aggregate types. And typically what we say is that these aggregates, if we're forming records or tuples, they are heterogeneous. That means we're allowed to put values of different types into these components. And in languages like Pascal, we explicitly say what kind of components we can put inside those aggregates. So we very specifically and explicitly specify that the first name and the surname of an employee should be a string, and we specify that the address should be an array of strings. And 3-element array here, 3-element array of strings. In Pascal, by the way, you can specify the upper and lower bound of an array. Index in the syntax, and we talked about these arrays on the next slide, I guess. No. In C, you have structures, structs. They are very similar to these records. They allow you to aggregate components into units, into separate units. SML, the same thing. We have tuples. So the star lets you define a tuple. The point is, in this case, the result of the Cartesian product of of real times real. That means you can write tuples in this form, just using mathematical notation in SML. And there are specific selectors connected to these tuples. So hash 1 is the selector for the first component of the tuple. I guess first component, right? Numbering them from 1 to n. Hash 1, hash 2, hash 3. I don't think hash 0 is allowed. Another kind of aggregation are container types, and here I'm more specifically talking about homogeneous types. So arrays is the typical example. So here the intention is that we we aggregate values of the same type into the bigger structure. So an array in C is declared by giving a particular type, in this case int, and you specify that all the components of this array should be of that int type. That's also an aggregation, but now homogeneous aggregation. Other container types, we have dictionaries, lists, set, tuples in various languages. Functions are types in programming languages that let you manipulate functions as first-class values. Other languages provide function types in the shape of pointers. So in C, for example, you don't have functions as first-class values. You don't typically return real proper functions from functions, but you can deal with functions using pointers, using references. I should say a bit about that restriction. In C, functions are not implemented in the way you've seen it in the CSE machine. In C, in the most common standards of C, functions do not carry an environment. You've seen these closure objects that we have in the CSE machine. That means in the languages that combine functions as first-class values with flexible scoping, and a function needs to be associated with an environment. In C, the design of C makes sure that that is not necessary. So we don't need to associate an environment with a function, and that makes it a lot less attractive to deal with functions as first-class values. They are this notion of closures adds an expressivity to the language that we don't have in C. So there is a trade-off of expressivity and efficiency. In C, the designers chose not to support this notion of functions as closures, and therefore, you have certain efficiency benefits, but you also have less expressivity. So C programmers will actually not very often make use of function pointers because of this restriction. But in languages in which you have proper functions as first-class values, that means in which functions refer to real closures, including environments, the resulting expressivity leads to often quite a prolific use of these functions. For example, in JavaScript, functions are heavily used when we're dealing with network programming, right? So you are typically referring to delayed execution using functions, or or promises. These are all different ways of expressing, a variance of expressing a computation that can be invoked later and that carries its own environment with it. In functional programming languages, you can make these function types explicit. That means you can describe a function type using a language of types. So this is an example in SML. SML lets you declare a function twice that is applied in this case to a function that takes an integer and gives you an integer, and as the first argument of twice, and you have an integer as the second argument of twice, and the function twice returns an integer, and it computes that integer by applying the function twice to its argument. That's an example. Other examples, you have you can explicitly give a name to a type in many languages. So here's another example in SML. So you give the name int function to the type int to int. That means functions that take an integer and return an integer. And then you can do things like this. You can define the square function. And now the system knows that the function square has the argument int. It has the body x times x. That means the result type is int also. Integer times integer should be an integer. And that means this language or the system will know that the type of square is consistent with this int function type. So you can think of square having the type int function. And we assign the name f to square. That means f also has the type int function. And therefore, it is possible to define a function evaluate that takes an int function and a value and applies that int function to the value. And you can apply evaluate to f now because you know that f is consistent with the declared type of the evaluate function. So f has a type int function, and therefore it can be applied. Therefore, evaluate can be applied to f. So here we get already a bit of a taste for what is happening when you can declare types in programming languages. There is this checking happening, right? So this system, the compiler, the system that implements the language can check that the names that you're using in your program are used consistently with the types that you declare them with. So that's static typing, and we're looking at that in a couple of minutes when we look at the typing strategies. There are such things as function types in C. I mentioned function pointers, so you can actually declare an int function pointer type in C, and you can do the same thing as you've seen in the previous slide. You can say f has the type int function, and you assign f to square, whose type declaration is consistent with the int function type. And the fact that it's a pointer doesn't seem to bother the type system here. So int function f declares the name f to refer to this int function pointer type, and you're allowed to assign f to the square function. And so this evaluate works just like this in C. And the only difference is that in C, in the usual standards of C, we cannot put functions inside of other functions. We cannot describe interesting environment structures using nesting of functions. But yeah, you can work with function types like this using pointers. We're looking at operations on types that allow us to generate new categories of types. And we have seen aggregation as a way to generate new types. And here is another way of generating new types. That's called union. I can form a union type out of two component types, and the result is not an aggregate value. The result is not a value that has multiple components, but the result is a single value that allows all the values of the component types as its elements. So we allow combining two types into a type that contains all values of each type. So here is an example in TypeScript. The vertical bar lets you form the union of two given types. So here we have number and string. So the argument A of the function combine here is not meant to be a tuple. It's not meant to consist of two components. No, it's meant to be either a number or a string. So that's the union type. The vertical bar forms the union of two given types in TypeScript. And this, in some languages, this is done using tags. So we have seen the data type declaration in SML already. And in the context of enum types, here is a bit of an extension of this. We can form a union type in SML by describing a data type that identifies each of its components using a tag. So this tag isInt is placed in front of an integer if you want to include an integer in your data type int or real. And you put isReal in front of the actual value if you want a real number. That means later on you can do stuff like this then, right? So you can pass an arg. You can describe a function to string, and you can pattern match according to the tag. Right? So this is a way to write functions very conveniently in SML that take such a data type as argument, and you use the tag to differentiate the different cases. So here isInt, the pattern isInt I matches elements of this type that are tagged with isInt, and we know that I then refers to an integer. And therefore we can apply the int to string function to I without a tag. Another operation we can see languages allow on types is intersection. So that's sort of the inverse of the analog of union. The that lets you intersect two types. For example, interfaces in object-oriented programming, we'll talk a bit more about next week, let you constrain type to the intersection of the two types. So here you in TypeScript you describe two interfaces, student and employee, and you can describe a function study for example, that is supposed to apply only to the intersection of the two given types. That means you have you're restricting yourself to classes, to instances of classes that implement both of these interfaces, and you restrict yourself to that group of objects. Using the ampersand. All right, let's talk a bit about typing strategies. So the elephant in the room, the big question in your mind should be now, when exactly does this typing come in? And there are different strategies that languages provide here that we need to talk about. So we know that data in computers is inherently untyped. That means sequences of zeros and ones. And if you're not careful, you might think, for example, a float is an address, and bad things happen. So what do we do about this? There are different strategies. First thing is the operating system can handle this. So turning a float into an address is a terrible thing because it will compromise your system. You could actually access areas of your memory that is not even part of the process that you've done. So it's really bad. But the good thing is that today's operating systems have provision for this, and they prevent these bad things from happening. That means they segment the memory into nice areas, and they allocate for each process which area in memory they can manipulate. Not only that, they can also specify which area of that memory is read-only and which area can be written to. So that's all very nice, and the operating systems then provide this service that the really bad things don't happen at runtime. Namely, that your data is compromised and that you actually have a security vulnerability. So the operating system makes sure that a process that wants to do these bad things crashes and is terminated as a bad program and eliminated from the pool of processes. That's a good thing. Segmentation fault is a good thing. It protects your system's integrity. That's one way of handling these type errors. So the operating system imposes this constraint on us that floats shouldn't be treated as addresses. At least those floats, when taken as address, will take you outside of the memory area. But still, you shouldn't be lucky, and a particular, or unlucky, a particular float refers to a read-write segment that belongs to the process that is executing. And then bad things from your program's point of view can happen, but not from the overall system's integrity point of view. So segmentation fault occurs when the process attempts to access memory beyond its given permission. And it's a safety feature of operating systems. Segmentation faults are fatal. That means they eliminate these bad programs from the pool of processes. So that's one way of using type information at runtime to protect the system. When am I saying that this is type information? Well, at some point, your program will figure out that your data is supposed to be an address. So in that sense, the underlying the processor treats this particular data as an address. So this sequence of bits becomes typed at that point when the instruction gets executed. And at that point, we're using that type information to protect you, to protect the systems. Another layer, another approach is dynamic typing. So here we have a layer of protection that doesn't live on the level of machine instructions, but it lives on the level of a runtime system. So here we're talking about, roughly speaking, interpreted systems. Systems that are implemented not by compiling them to machine code, but by executing them in a runtime system. That could be a virtual machine, but it could also be an interpreter. So these runtime systems can impose type constraints. They can protect us at runtime. And they can do a lot more things than what the operating system can do. The operating system and the underlying computer has very little information about what kinds of operations should run. But the runtime system is tailor-made to execute programs in a particular programming language or in a particular virtual machine language. So it can be much more sophisticated and can respect a type system. So type checks in these runtime systems can be done at runtime, and type errors then are runtime errors. And such systems ensure the safe execution of programs. That they prevent, for example, such segmentation faults. And they can prevent all kinds of other errors. They can prevent that a record is used as in place of a function, for example. You want to apply a function f, and at runtime you figure out that f actually refers to a record, or f refers to an integer. Using the machine instructions, or using the virtual machine or the interpreter, without this protection could lead to all kinds of errors inside the virtual machine. Errors that could have similar severity as a segmentation fault. And a runtime system can prevent these errors. So that is called dynamic typing. So here we make use of type information at runtime to prevent bad things from happening and to protect you. And the disadvantage of this is that type-related errors can occur after the software is shipped, right? So you do all your testing, and then you ship your software to the customer, and eventually the place in the program where this type error occurs gets executed, and that is not covered by your test cases, for example. And you get a runtime error. So that's a disadvantage. Another disadvantage is that we need to carry along the type information into the runtime. That means for dynamic typing, types are associated with actual runtime values. We need to keep track of what is this, what type is the particular value supposed to have. And we need to carry that along in our computations. So that means if we want to protect ourselves, we need to keep that information, that is memory intensive, but we also need to keep checking that information. Is this a function before we actually apply the function? And that is time intensive. So dynamically typed languages are carry with them an extra burden in terms of time and space consumption. And the implementers of Python, for example, or the implementers of the JavaScript runtime systems or the Java virtual machine, they're working very, very hard to reduce that overhead, that type-related overhead that we have with dynamic typing. But it's possible to reduce that type-related overhead. So really heavy-duty engineering allows these implementations to get to eliminate almost all the overhead. So if you look at the V8 engine inside of your browser, inside of your Chrome browser, it can execute JavaScript to a speed that is actually not that far from C, from comparable C programs. So it's possible to reduce this type-related overhead at runtime with heavy-duty engineering of these runtime systems. Another approach is called static typing. That may be a bit more standard. It may be a bit more what you would expect in this kind of lecture. It is not to associate types with the actual runtime values, but to associate types with names in your program. So we are now declaring that a particular name in the program is supposed to have a particular type, and we are checking the consistent use of these names throughout your program before we even deal with the program, before we compile it or before we interpreted it. And that is done as a type checking. So we are checking the consistent use of these types that appear in the program before execution. We do that often at compile time or before compile time, to ensure before the programs are run, before they're even compiled, that there are no type errors. And usually this is combined with some dynamic type checking. So you don't want to impose type restrictions in some cases. For example, it is not practical to remove the possibility that a particular number might become zero. The type system is not strong enough to remove that possibility. And yet you want to have x divided by y. Y could be zero at runtime, and in some languages that is considered a runtime error. So we want to keep that to the runtime, or array indices out of bounds. You want to do index computation. You want to have the full flexibility of arithmetics to compute with your array indices, and yet you want to protect your arrays from being accessed out of bounds, because that could lead to really serious stuff. So the compromise is to add some runtime checks to these operations, array access operations. So we can statically figure out that the index is an integer. We can statically figure out that what we are trying to access is an array, but we cannot, or we don't want to statically figure out that the index is accessing within the bounds of the indices of the array. That is a runtime check. So that's a compromise. between static typing and dynamic typing in the case of arrays in most languages. And there's this is associated with the discovery. So this notion of really strong typing originated in the 1980s in the context of these functional programming languages. So the functional programming languages were the pioneers of strong static typing. And this was particularly important because the expressive power of functions allows us to write wonderful programs that are, for example, that do symbolic processing. In the old days, what we used to do as AI was heavy-duty symbolic processing. So very fancy data structures with functions inside of them can express complex ideas such as expert systems, for example. And these languages are very good at expressing such complex abstractions. And this became possible because of these very strong type systems. So the experience was that if you add a type system, a static type system, to such expressive languages, you get an order of magnitude of productivity increase compared to dynamically typed languages. So that means if you program a particular expert system in Lisp versus you program it in SML, you get an order of magnitude productivity gain by using SML or using a typed programming language. And I think that people realized that over the years. So Robin Milner was a pioneer in this. Well-typed programs cannot go wrong. And for me personally, that was also a revelation. I started programming in these at the time, considered very high-level programming languages. And indeed, the experience is, no matter how sophisticated your abstractions are, once your program passes the type checking, most of the time the bulk of the work is done. And that may be consistent with your work with Java, for example, right? If you're writing interesting processing in Java, and it's not a question of getting the algorithm right, but getting the overall logic structure right, the overall abstractions right. Once you pass the type checker, you know you are in business. Yeah? So that's sort of the observation. Well-typed programs cannot go wrong. It's a blunt and very broad statement, but that's what it means. It means that you are well placed in your game to make your program work once you pass the type checker. I have some theory for you here, and I would like to establish a couple of things. One is the notion of well-typedness versus type safety, and we also will look at weak typing a little bit. So, a type system is a system that lets you do static type checking. It's a formalism that allows us to describe constraints on the kinds of programs we can write. And these constraints are checked at compile time, at the time of, or even before we compile the program by type checker. So type system assigns types to names in programs, not just names, but also expressions. And they describe sets, the sets of values that are elements of the types, right? So the richness of the type system determines the complexity of typing. So we have that spectrum. The richer, the more expressive the type system is, the more kinds of constraints we can impose, the more difficult will it be to check that your program actually adheres to this type system. So the first term that I would like to define is the notion of well-typedness. Well-typedness describes a particular program with respect to a particular type system. You take a program and you apply your rules of the type system, and the type system can tell you okay or not okay. There are type errors or there are no type errors. So well-typedness is a property of a program with respect to a type system. And overall, well-typedness describes the set of programs that are well-typed, right? So that means you take the set of all programs, and the notion of well-typedness filters out those programs that you don't want to consider, that are bad programs. You throw them away, or you tell the user this is not a good program. So try to improve your program before you can come back and try compiling the program again. So that's well-typedness. And the strictness of the type system determines how small that set of well-typed programs is. So the stricter the type system, the harder it will be to pass these tests. What I would like to contrast well-typedness with is the notion of type safety, something entirely different. That's probably the most important lesson of today's lecture. So well-typedness is not a property of a particular program. Type safety is not a property of a particular program. Type safety is a property of a programming language. That means the set of programs along with the runtime system, along with the type system. So type safety describes, in other words, the relationship between a static type system and a runtime system. So we can say a programming language, together with its type system and its implementation, or its specification, is type safe or not type safe. So type safety is a property of a programming language combining static semantics, typing, and dynamic semantics, basically execution, specification of its runtime. So a language is type safe if well-typed programs don't do bad things. So well-typed programs shouldn't treat a number as a function. Well-typed programs shouldn't apply a function, a binary function to 3 arguments. So languages in which well-typed programs don't do a specified set of forbidden operations are called type safe. And a special case of type safety is memory safety. So if well-typed programs don't access memory in ways that are not consistent with the data types in the program, then we have achieved something. We have systematically prevented a certain class of runtime errors using a type system. So you see, the notion of type safety is a very general notion. And depending on how you define these forbidden operations, you can achieve type safety with different means. If you're only interested in memory access, for example, you just need to make sure that your memory access follows the data structures that your programmer constructed. So for that, you actually don't need time. So in Scheme or JavaScript or Python, you can guarantee type safety even without a type system. And you can guarantee memory safety even without a type system. Yeah? Because the runtime system prevents, or the runtime system ensures that all memory accesses follow the constructions that are done by the programmer. The programmer constructs data structures, and your data structure accesses need to follow those structures. And that means you don't get into memory areas that are not safe. So memory safety is an example of a very general type-related concept, a type safety concept, that we can handle in runtime systems, that we can handle in a program language implementation. And again, imposing specific discipline. For example, the discipline of pointer arithmetics, right? So these languages don't allow you to directly manipulate pointers. That ensures memory safety. And the array bounds checking is another example of a language constraint, a dynamic constraint that we impose on the programs to prevent bad things from happening. So if you look at the history of programming languages, we actually see a history of more and more expressive type systems. There is Mark Manassi, who came up with this statement. The fundamental problem addressed by type theory is to ensure that programs have meaning. Right? We want to make sure programs have meaning. The fundamental problem caused by type theory is that meaningful programs, in our mind, meaningful programs, may not have meanings ascribed to them by the type system. The type system may be too restricted to assign them the meaning that is in our mind. So again, it's a mismatch between what is in our head and what is implemented by the system. And that leads to a quest for richer type systems. So we want to have more and more expressive type systems to match our idea of meaningful programs to the idea that a type system has of programs to which meaning can be assigned. And this meaning is assigned using a type system. More specifically, meaning is assigned to programs by assigning a type to every identifier and expression in the program. That's the idea of type systems. So we can then talk about, so that's basically the notion of type safety. And I think I should take you back to this. We will play with this more in the homework, in the assignment. But the example of SML should show you what is happening here. When we are before we execute the program, so before we actually run this program, including we try to run this application of evaluate 2F and 3, we run a type checking phase of execution. So before we run or before we even compile, we type check the program. That means we're not in the business of actually executing the program. We just look at the program statically, we look at the constructs, and we run a particular algorithm. So this algorithm follows typically the syntactic structure, the syntax tree of the program. Yeah, remember syntax tree from the syntax? Yeah. So it will go component or construct by construct and apply a particular algorithm to it. So you can think of this here. You actually have the type declarations. So those are components that this type checker needs to keep track of. There needs to be a mapping in the type checker from these names, such as in function, to the declared type. So this mapping in function to int arrow int is going to become part of the state of the type checker. The type checker needs to make that association so that when it later encounters an application of, let's say, f, of the function evaluate to f, it can look up, what is the type of f? F has the type, must have the same type as square, and square is a type from int to int. So f has type int to int. How does it find that out? Well, it goes through the structure of the program. It sees the function square, and it type checks the function definition of square. That means it associates x with int before it goes to the body. The body of the function, x times x, is being type checked with respect to what? Remember? When we actually run programs in our CSE machine, we have a current environment. We have an environment that maps names to values. When we're type checking, we actually don't care about the values. What we care about is the types. But we have something similar to deal with, right? We need to map our names to the declared types. And that's what's happening actually in our implementations of type systems, for our type checkers. There are corresponding structures, not environments, but type environments that map names to types. And that's what we're going to do here. When we enter the body of a function, of the function square, we extend the given environment that we have by a binding of the name x to the type int. And then we can go through the body of the function to see that all declarations match, all expressions are consistent with the types. And that includes evaluate, the body of evaluate, applies g to value. G is known as an int function. Our type checker can then look up this int function and finds out that it's actually the type of int to int. So G has the type of int to int, value has a type int, G applied to value cannot be type checked because we have a type environment in which G as a type, namely from int to int, and value as a type, namely int. That matches, right? The argument type of G matches the actual argument value. And we know that the result is int, and that is also consistent with the declared output type, which is also int. So that means our type checking of the function evaluate is successful. We know that when we know that all names in this function are used consistently with the declaration. That is what a type checker does. Okay, so that is roughly speaking how type checking works. And languages are more or less, language implementations are more or less sophisticated in how elaborate this type checking is. And we'll talk about that in a few minutes in our advanced topics. So this is just to give you an idea of how the type checking actually works. You need a notion of type environments, and you need to have a lookup table that maps declared types, such as int function, to what they refer to, namely the type description. So that's well, typeness, weak typing. What do we have for weak typing? It is pointer arithmetics. So in C, what you can actually do is you can apply arithmetic operations on a pointer, like here. So you increment a pointer, and you keep accessing the pointer using the array index 0. So the pointer is treated as a number, and at the same time as the address of an array, and that is just fine in C. So pointers are arithmetic operations are allowed on pointers, and that gives you expressive power, gives you convenience as a programmer, but it comes at the cost of runtime errors, because C is meant to be a systems programming language, so operations like this are directly mapped to machine instructions. There's no checking going on, no bounds checking happening, and that means if you're not careful, such operations can immediately lead to a segmentation fault. When your pointer arithmetic goes wrong, you end up trying to access an area that you're not allowed to. All right, let's look at some advanced topics. The first advanced topic that I have listed here is recursive types. So it is possible in many languages to recursively describe types. So here's again an example from XML. You have a data type int tree, and an int tree is either the empty tree or a node that has an integer, and that has two subtrees that are themselves int trees. That allows you, that's a recursive definition, and allows you to describe the structure of trees. Very convenient. And if you're familiar with lists, for example, in Scheme, they are recursively defined in that way. So you want that recursion. That's a nice expressive expressivity that you can get there, if your language supports this. The second advanced topic is generic types. So here we would like to allow that that operations uniformly apply on their arguments, regardless of what these arguments are in detail. So here's an example. You have a map function, again in SML, and the idea is to have a list again recursively defined as either null or a pair whose head is some data value and whose tail is another list. So that's sort of a linked list data structure. And we actually don't care that much what kind of data we have in these lists. So there should be, we have this understanding in our mind that we know what a list of something is, a list of some unspecified type. It is either null or a pair whose first component has the correct type and whose second component is another list of that thing. So that means we can describe operations on such generic types, such as map. So map takes such a list as a second argument, and as a first argument, it takes a function. A function from something to something. From some type to another type. And we don't need to specify what those types actually are. The map function doesn't care. The map function takes this function f and applies it to every element of the list. But we have a lot of information when we do that. So here's the type of map. The type of map is, of course, a function type that has a function, a unary function as its argument. First argument. That means that's functions that take some type A to some type B. So the result of applying the function f to something of type A is something of type B. And with that assumption, we can apply map to an A list as its second argument. And the result is a B list. So map takes a list of A's and applies F to each element so that you get a list of B's. Right? So A and B can be any type. And that's a generic type. So map has a generic type. You can think of these as A and B. You can think of A and B as parameters, not referring to values, but referring to types. So we parameterize a given program with respect to types. So that's what has become known as generic types. In the old days, we would call this parameterized types. And this is, of course, very popular. All the languages provide this now. You have generic types in Java and basically all modern programming languages. I should mention the notion of type inference in this context. See, when we talk about static type checking, we need to analyze a given program. So here we know that x is supposed to be a number, and its result is y. It is assigned to y times 4 plus z. So from this, we can derive a requirement, so the notional class, let's say in TypeScript, you can apply plus to 2 strings and you get a string. You can apply plus to 2 numbers and you get a number. But this particular expression, y times 4 plus z, requires that the result of this operation is a number. And that means y needs to be a number and 4 plus z needs to be a number. And if 4 plus z is a number, then z should be a number. So we can actually derive constraints from such arithmetic operations. So in some sense, a type checker is always a type inferencer. A type checker always infers types of components, of expressions. So we infer that z needs to be a number. And the question is then, how sophisticated are these type checkers? Are these type inferencers? And a very powerful type inference mechanism was invented in the 1980s. Damas, Hindley, Milner. Type inference is a type inference algorithm that was specifically designed for higher order functional programming and can deal with recursive types. So it's a type inference algorithm that then became standard in functional programming. And a central component of this Damas, Hindley, Milner type inference is the notion of let polymorphism. So we want to make sure that the result of our type inference is not constraining us unnecessarily. Let's say we have inferred that map has the type A to B, A list to B list. That's our generic type for map. Now, when we apply map in different places of the program, we should not impose further constraints. So the fact that we applying map to a function from, let's say, int to int and an int list should not impose constraints on the use of map later on. So that is called let polymorphism. See, we assume that the name map is introduced using a declaration. And that, let's say, is done using a let. Remember let from JavaScript, right? So let, it's a declaration of the name map. And Damas, Hindley, Milner makes sure that this is a polymorphic declaration. That means when we figure out that this is a parametric type, that map should be associated with a parametric type, the uses of map should instantiate these type parameters independently. And that's not the case for other kinds of declarations. So for example, if you have a parameter of a function, and you figure out that the parameter is of a particular generic type, we need to impose constraints on those parameterized types throughout the function in which the name is a parameter. So not all declarations should follow this let polymorphism. So, and the details are a bit beyond this course. So we take it that the notion of generic types corresponds to particular typing issues when we are dealing with type inference. And our assignment will go a little bit into the details without actually asking you to understand this particular type inference regimen. So we get a feeling for type inference and for let polymorphism without having to understand it in its gory details. There is a recent phenomenon in programming languages called gradual typing. So we have discovered that in programming languages, we have discovered that static typing is often a bit restrictive. We have programs in our mind that don't pass static type checkers. So we want to combine static and dynamic typing, as we have seen in various examples in this lecture, array bounds and so on. And we want to have static and dynamic typing coexist in a fruitful way. So we check and infer types before running as much as possible, and we include runtime checks for open dynamic expressions. And we intelligently make use of inferred types even for runtime checks. So I hope this is an example where we have a logical value if it exists, log value, log value if it exists. It's either string or undefined, and we can then check that the type of value is string, and we can do something interesting. For example, we can use string interpolation in a backwarded string. Yeah, so this is an example for TypeScript making use of an explicit type check to infer information and push it down in a particular branch of the function in this case. So this branch has richer information about the type of value. In a different branch, you still have the union string union undefined. In this branch of the conditional, we know that value has the type string. And we can make use of types for optimization. So type-safe languages allow omission of runtime type checks often and quite systematically. And that means that languages such as OCaml, Haskell, they are actually often outperform C, which is sort of the benchmark in the runtime of executables. In dynamically typed languages, type information is used at runtime to gain execution speed, so you can have runtime specialization. So you can exploit these annotations, the type annotations you carry along to the runtime to optimize your programs during execution. So this is just-in-time compilation, for example. You could have a particular branch in which you have runtime information of the type of particular values, and you can specialize your program with respect to that runtime information, generate specialized code. That's called runtime. That's called just-in-time compilation. All right. So we come to an end, and next week we're looking at data types. We're looking at allocation techniques, stack and heap allocation. We're looking at references and pointers, and eventually we get to object-oriented languages, where the notion of types will reappear. So in summary today, we have seen that Compilation and interpretation can include type checking. So we can have type checking as part of a compiler. So we do static type checking before we even compile or run the program, or we can make use of type information at runtime during the interpreter in a virtual machine. Types are to make errors occur earlier before they cause more damage. You've seen a very simple example of a segmentation fault. You don't want to have unsafe access, so you make the error less bad. You cause less damage. And the same for types. So types are there to make errors occur earlier or to incur less damage. So even when you have a dynamic type checking, the result of type checking is to safely terminate the running program as opposed to doing unsafe operations at runtime. And static type checking takes this even further and prevents the program from even compiling and let alone shipping to the customer before it passes the type checking. Earlier can mean compile time or runtime, and if it is runtime, and if it is compile time, we're talking about static type checking, and if it is compile time, we're talking about static type checking, and if it is at runtime, we're talking about dynamic type checking. We've seen strong versus weak typing. Strong typing refers to guaranteeing that certain kinds of errors do not occur at runtime. And we do that using a type system that is typically formalized and proven correct, hopefully. And weak typing, we do sort of a best effort to prevent errors. Type systems formalize this process, and we've seen the notion of well-typedness versus type safety. Well-typedness is a property of programs. Type safety is a property of programming languages with respect to their static and dynamic semantics. We've seen that we can infer types. We can actually extend the notion of type checking to systematically identify what types particular expressions in programs have. And we take a closer look in our. Any questions about type checking?